Finally, we're to the point where we get a look at our first geometric two-column proof. So we're just going to look at an example that kind of takes us through the process, real basic example that'll get us started. So for any proof that we write, we're going to start off with three things. Sometimes they'll be given to us, and sometimes we'll have to create them on ourselves, depending on what we're trying to prove. So in this case, we're just going to be given one. So the first thing is we need a diagram. So let's say we have a diagram. It's just going to have a segment in it. There are going to be 3 points. I need to start with a diagram, and then I have two statements, or two sets of statements that I'm going to be given. One of them is just called the givens. So these are the things that it's like my starting information that I'm going to begin with. And then I also need to figure out what my goal is to actually prove. So in this case, my given is that the distance between A and C is the same as the distance between A and B added to the distance between A and B. And what I'm trying to prove then is that AB, the distance between A and B, is equal to the distance between B and C. So that's what I'm trying to show using this diagram I have in front of me. So how I set this up is we're going to create what's called a two-column proof. So I'm going to start with this T-chart here. And what goes into my T-chart, that was poorly done. What goes into my T-chart is a set of statements on one side. So these are going to be the things that kind of lead me to my conclusion, of which the last one is always going to be this statement that we're trying to prove. And then on the other side, I'm going to give my reasons. Oh, I switched shades of blue. Oh well. I'm going to give my reasons. And all these reasons will be things from our toolkit. So these can be things like definitions. They can be properties. They can be postulates. Or they can be theorems. And so we're basically just going to draw from this set of 4 things, and all my reasons have to be one of these. These are things that I can't make up. The statements I'm going to make up depending on what the situation is, but the reasons always have to be one of these predefined things. If it's a definition, I'm always going to put this in if and only if form. If it's a property, I'll usually just state the property that it is. And then if it's a postulate or theorem, I'll always put it into if then form, except for two situations, which you'll actually see here in a bit. So what I'm going to do is I'm just going to step-by-step logically prove that this statement right here is the case. That is my goal. And the way that I'm going to do that is by, of course, just starting with my given. That is my first statement, that AC is equal to AB plus AB. I'm going to number this. This is statement number 1. And then I'm going to associate it with a reason. So this reason number 1 is just that this was given to me. So now I have to kind of logically think. So I haven't put any thought into it at this point. But now I can start to think about where I'm actually trying to go with my proof. So before I write anything down, I should really be thinking about where I'm going with this. So it tells me that AC, this entire length here, is equal to AB plus AB. In other words, what it's telling me is that AB is half the length of what AC is. And so I need to use that information somehow to say that AB, the distance between A and B, is equal to the distance between B and C. And so what I'm thinking about is trying to link these together somehow. I know that the distance between A and C, I can represent that in a different form. I know that AC is equal to, well, AB plus BC. And so I'm going to try and use that to my advantage somehow. So I'll actually start with that. I can make this statement that AC is equal to AB plus BC. The question is why, and we'll get to that in a second. But I'm going to write that to start off with. So this is AC is equal to AB plus BC. So this is statement number 2. I'll number it, and then I will give my reason. And so why do I know this to be the case? And so I have to think about here, this comes from a definition, a property, a postulate, or a theorem. And so my definitions don't really help me out here because I'm just talking about segments. There's no property that helps me out, and we haven't learned about theorems yet. So postulates, and it has to be a postulate. And so there is a postulate that tells me this. So this postulate that tells me this is the segment addition postulate. And so that's going to be my reason here, the segment addition postulate. Now, normally I would state my postulates in if-then form. Segment addition of the postulate is just a special one that's kind of weird to state in if-then form. And so this is one of the two that I'm just going to give a name. The other one is the angle addition postulate. So normally what I'd have to do here is every reason that I give will connect it back to something I've said previously. Segment addition postulate is unique in that way as well because I'm actually connecting it back to the diagram. We'll see here in a second what that looks like if I'm connecting back to a previous statement, but for right now that's all I need. I can say that AC is equal to AB plus BC because of the segment addition postulate. So every statement that I give is going to be backed up with this reason. It's telling me where it's coming from. So my next statement then, I have to think about what I can do next. So what I can do next is, my goal is to get an equation here that just has AB and BC in it. And so I'm really close. I have two equations here. One has AB in it, the other one has BC in it. And so if only there was some way that I could combine these two statements into one, and there is a way. And it's because both AB and AB, and then AB and plus BC, or AB plus BC, are both equal to the same thing. And so we actually have a property that tells us that these two things will be equal to each other then, and that's the transitive property. So I can make the statement that AB plus AB will be equal to AB plus BC. And the reason for that is the transitive property. So properties we're always going to write by name, and so this is one of the ones that we just learned about, the transitive property. And what it tells me is that whenever I have two things that are equal to the same thing, they're going to be equal to each other. Now, this statement here goes to this reason, and so I have to ask myself, well, what statements did this draw from? And it drew from statements 1 and 2. So what I'm going to do now is cite where this came from. So whenever I'm using a transitive property, I should always be citing two things, the two statements that I'm linking together. Because every statement that I'm giving is using a reason that's linking together something that I've said previously. So in this case, it's a transitive property. And so I can make the statement that AB plus AB is equal to AB plus BC because in statements 1 and 2, if I link them together using the transitive property, gives me this equation. So now I'm really close. I'm really close to the statement that I want to get here, which is AB is equal to BC. I just need to do one more thing, and that's I need to get rid of these ABs. So what I'm going to do is, now we're just kind of back to some algebra. I am going to subtract, I'm going to subtract an AB from both sides. So I'm going to subtract AB from this side, and then I'm going to subtract AB from this side. And what allows me to do that is the subtraction property of equality. Now this is something that we didn't do before with our algebraic proofs, and the reason we didn't do it before with our algebraic proofs is because they were just linear. Just one statement went to the next, went to the next, went to the next. But now there's going to be situations where our reasons are linked to things that weren't necessarily the previous statement. And so I'm going to give a citation for this, and it's going to be the previous statement, and that's statement number 3. Okay, I started with statement number 3. I used the subtraction property of equality by subtracting AB from both sides, and then I got this new statement here. And so now I'm basically done. I just need to follow through and actually do this. So AB minus AB is, of course, just 0. So AB is going to be equal to BC, which is what I wanted to prove. And so this matches my proof statement, so that means it's going to be my last thing. I'm done. I just need to give a reason for that. And my reason, of course, is that I was simplifying. So this is just simplification. Okay. And where did that come from? That came from statement number 4. So this is what a two-column proof looks like. I have a set of statements backed up with a set of reasons. And so I want to draw your attention to one more thing here, and that's the fact that every statement that we give comes from the reason that's attached to it, and then a lot of times a previous statement. Now we're just given this so it doesn't match back with anything, but then my segment addition postulate is where I get this from, and usually this would be a previous statement, but in this case it comes from the previous diagram. So it's a combination of this reason and the previous diagram. Then when I move on to statement number 3, it comes from the transitive property, which was linking together statements 1 and 2. So the combination of statements 1 and 2 with this reason gives me my next statement. Then I moved on to use the subtraction property, so that reason gave me this statement linked together with the previous statement, and the same thing here when I'm simplifying. I use simplification in the previous statement here to give me my last one. So every statement that I give should be, unless it's being taken from the diagram, just linked with something that came before it, and that reason should back it up. So this is a real, simple example of a proof that I have here. It's a great place to start and gives us kind of an idea of what things are going to look like moving forward.